Good morning everyone, Dr. Bennett here and welcome to the second in a three-part little mini-series looking at airplane takeoff and landing modeling. So in this little video we're going to consider the landing model, which is going to follow a number of similar assumptions to the takeoff model, just with a few key differences which I'll be sure to kind of emphasize here. So for the landing model, here's our airplane. Again, we're going to be focused on primarily calculating the landing distance required. So we're assuming that that distance is from the point of touchdown, so the point at which the wheels first touch the runway, to coming to a dead stop, so stationary at the end of the runway. So the forces acting on the airplane are described in this little diagram right here. And again, I've color-coded the forces parallel to the runway in red, and the forces perpendicular to the runway in blue. So let's start with perpendicular. We've got lift force acting upwards, as with the normal force. And then we've got the weight vector acting vertically downwards from the CG position. Then, parallel to the runway, we've got the drag vector here, and then also this term which takes into account the braking coefficient. Now this is not to be confused with the rolling resistance coefficient that we had in the takeoff model up here, look. So in this context it means a slightly different thing, because now obviously we're applying wheel braking and the rolling resistance to help us slow down. So it's given the same symbol, mu, but for the landing context it means a different thing. So this is going to be our braking coefficient, and that's going to be significantly larger than our rolling resistance coefficient, so somewhere in the order of about 0.5 for a dry runway, somewhere in the order of about 0.25 for a wet runway. So again, using Newton's second law, summing forces both parallel and perpendicular. In a parallel direction we've got F equals ma, so we've just got d plus mu n, so both of those two forces are helping us slow down, they're helping us to decelerate, right? We're assuming that we've got no thrust term, so we're assuming that, okay, we pull the throttles back to idle to help us decelerate. If we have the ability to reverse thrust, then we would have a reverse thrust term in this equation as well, again acting in the direction associated with these two terms as well. Then summing forces perpendicular to the runway, we've got positive L, positive normal force, and then negative weight. And so again, this v squared over r represents our centripetal acceleration, so where r is like the radius of the arc if the airplane is pitching or has a circular flight path, let's say. But if we're decelerating along our runway horizontally like this, then the radius of that arc tends to infinity, and so again this part here will be 0. And so then we can just rearrange this equation, n plus L minus W, to just give us the normal force, which is just the difference between weight and lift. So then we can derive an expression for the landing deceleration from the first equation up here, F equals ma. So m, the mass of the airplane, is just the weight over the acceleration due to gravity, specifically the landing weight, which I've designated with the subscript L, multiplied by the landing deceleration, A sub L. So d plus mu n from here, replacing n with this expression that we found from the perpendicular summation. So once we have that, we can just rearrange it for A sub L, multiply both sides by g, divide both sides by wl to get this. Then again, what we're going to do is derive the landing time required next again as a stepping stone to get us to the landing distance, and again that will be obvious in just a second. The key assumption that's different here in the landing model is that we assume that our landing speed is now 1.3 times the stall speed as opposed to 1.2 times the stall speed for the takeoff speed. And again, that's just a kind of 30% buffer over the stall speed for safety reasons, and that's the kind of conventional way that that's done. So in the previous video I showed you how we derive this expression here for the stall speed. It's where so v stall corresponds to CL max, and we just use the lift equation to get this expression. So if you're not sure where this kind of square root term comes from, just check out the previous video on the takeoff distance. So next, what we say is that the landing deceleration is just equal to the change in speed over time. And if we're assuming that we're coming to a dead stop, then delta V will just be V. And if we assume that we start our landing deceleration at time t equals 0, then delta t will just be TL. So rearranging this, t equals VL over AL. And so now we have expressions for both of these. VL is here, look, in the numerator. AL is the thing that we've just derived. So we'll just plug those two expressions in and tidy it up a little bit to get this. Now, as I said in the previous video, the time required is a little bit irrelevant. What we're going to use this for is to calculate the landing distance required. So that's over here, look. Landing distance is just the integral of the landing speed with respect to time, and if the landing speed is just equal to the landing acceleration multiplied by the landing time, then we can just integrate this with respect to t. A is just a constant, we can pull that out, so we'll just be left with the integral of t with respect to t, which will just give us t squared over 2. So then all that we need to do from this point to calculate the landing distance is just plug in our expressions for A sub L and T sub L that we calculated back over here. Here's A sub L, here's T sub L. And again, we're going to end up with a bit of a messy equation once we plug all of that in, but again, it tidies up quite nicely to give us this expression. So in particular, take note of this factor of 1.69 in the numerator here, which comes from this term 1.3 squared. So again, let's just have a quick whiz through some of the terms in this equation, because generally we're trying to minimize our landing distance again, because, well, that means we can utilize more airports and more airfields and runways and stuff, right? So to minimize our landing distance, we need to minimize terms in the numerator, maximize terms in the denominator. So obviously landing distance is minimized for lower weights. We've got our density term here again in the denominator, so we need to maximize that. That's maximized at lower altitudes, also for lower temperatures. Our landing distance is minimized for higher wing reference areas. So again, that's why certain airplanes have what are called Fowler flaps, which both alter the camber of the airfoil of the wing, but also extend the trailing edge to give us a larger wing reference area. So check those out if you're not familiar. Higher CL max, well, that's just determined by the airfoil, and then flaps, which will alter the camber as well. So that's an aerodynamic consideration. The acceleration due to gravity is lowest at lower altitudes. Again, a fairly negligible difference, but that's included there as well. We need to maximize D, so increase drag to help us slow down, right? That seems fairly intuitive, and again, that's why certain airplanes have what are called air brakes, just to add a bit of extra drag in there. As soon as we touch down on the runway, might deploy those. We need to maximize our wheel braking, because that's associated with this mu term right here. And finally, we need to because we have a negative term here, we need to lower the lift, right? And again, that's the reason why certain airplanes have what's called lift dump or spoilers, and what they do is basically deliberately spoil the lift, hence the name, right? And you might hear pilots refer to that as lift dump, and essentially they're just little flaps which extend from the upper surface of the trailing edge of the wing and just basically deliberately spoil the lift so that the airplane sticks to the runway and helps us decelerate as quickly as possible. What we don't want is for the wheels to touch the ground on landing and the airplane to start floating along the runway as we're trying to decelerate, because obviously that will negate our wheel braking here. So there we go, that's just a quick whiz through of how we model airplane landing distance. And in the final video of this little mini series, we'll have a look at some of the regulations specifically related to the rejected takeoff and how we figure that out. Thanks.